This is a capacitor circuit problem. So after solving it, hopefully we are going to illustrate some of the uses of some concepts that we have defined, especially this equivalent capacitance concept. We are going to make use of it in here. Hopefully we will also illustrate some of the important physical principles. Okay, let me quickly describe what happens in here. So first of all, we have these 4 capacitors connected like that, and they are initially empty. And after that, we just connect these 2 terminals to a 15-volt battery. And then after that, the battery is removed. And at this stage, we are going to compute the charges on each capacitor, the energy, and things like that. Okay. So after that, what we do is we just connect these 2 points with a wire. So in that case, it will appear that a charge actually flows between these 2 points, and so as a result, the charges are redistributed on the capacitor. So as a result, we will find the new charge distribution on each capacitor. We are just going to compute how much energy is lost. So we are going to see that the energy is actually lost in there, and things like that. Okay. So let me quickly show this. I think there was a summary in here of what's happening in here. So in the first step, we just connect these 2 terminals, A and B terminals, with a battery. We disconnect the battery. So the battery is disconnected, so that's the important part. So after that, the battery does not play any role at this stage. So at this stage, we are going to compute the charges on each plate, essentially. Okay. And then after that, we are going to connect these 2 points, and well, basically, we will then compute the charges on each plate and things like that. Okay, so I'm going to start with the first part in here. So after we connect the battery, charge the capacitors and discharge it. So disconnect the battery. Sorry about that. What happens? Basically, we have a situation in here where the potential difference between the points A and B is equal to 15 volts. So let me use a yellow color in here. So that potential difference is equal to 15 volts. And based on using this, we would like to compute the charges on each capacitor. So what we do is we just use this equivalence capacitance concept. So since this is a little bit complicated circuit, so what we do is we first simplify these 2 capacitors connected in series. So as a result, I need to find some kind of an equivalent capacitance in here. And we also simplify these 2 capacitors to an equivalent capacitance in here. So I'm going to call this as this one as C12, the equivalent capacitance, and this one as C34. Let's just remember that connecting them in series is equivalent to increasing the plate separation of the capacitor, so therefore the capacitance decreases, in which case we can easily remember that you're actually adding up the reciprocals of the capacitances. So in this case, this is like 1/6 plus 1/3, you get 1/2, so therefore the C12 is equal to 2 microfarad. And similarly for this one in here, so the values are the same, they are just placed in a different order. In any case, so on that branch to the equivalent capacitance is 2 microfarads. Okay. Then now we have 2 capacitors connected in parallel, and so as a result, let me write it as like C prime in here as the equivalent capacitance of everything in here, which is in that case we know that when the capacitors are connected in parallel, this is equivalent to increasing the plate area, which increases the capacitance value that corresponds to the addition of the capacitance values. So the total capacitance is 4 microfarad. Okay. At this point, we can go backwards. So I know that this potential difference between the points A and B is equal to 15 volts. And so as a result, for this equivalent capacitor, the charge on the plates is basically 4 times 15, that's 60 microcoulombs, which means there's a minus 60 microcoulombs on the other plate. But let's just leave it in here. Okay, so at this stage, we just go back. So what can we say about these 2 capacitors? There are actually two different approaches in here. The simplest approach is to actually look at this picture, see that both of these capacitors have the potential difference across their plates, which is equal to the potential difference VAB. So therefore, we have a 15-volt potential difference in here and 15-volt potential difference in here. So no problem with this. So as a result, this charge in here, I think I'm going to raise this. The charge on this plate of that equivalent capacitor is, I think I'm going to call this as Q12. That's equal to 30 microcoulombs. And this one too, so that's Q34. Let me just write what I'm writing in here. That's basically I'm multiplying the capacitance value with the potential difference across the externals. So therefore, this is 30 microcoulombs. Okay, just notice that the 60 microcoulombs on that equivalent capacitor is actually the sum of this charge plus that charge. Okay, so let me actually make this point more clearly. So here we have two capacitors connected in parallel, and so as a result, this is the equivalent capacitor for this configuration. What I'm saying in here is that the total charge on that positive plate of that equivalent capacitor is equal to the sum of these two charges in here, the charge on this one plus the charge of that one. So the basic idea in here is that you can think of this plate of that equivalent capacitor as the plate obtained by basically bringing these two plates near to each other. So they are very near to each other. So you basically make them very close to each other so that they touch. So eventually they become one plate, but without changing their total area. So in any case, in this kind of, if you think of it like that, then this is equal to this plus that, right? Think of it like that, and it turns out that the charge ratios on these two plates is the same as the capacitance ratio, since these two capacitance are both 2 microfarad. In that case, we have equal charges. So the 60 microcoulomb is basically divided into 30-30 in here. Okay, so let me undo all of these. I don't know why I'm undoing, but perhaps I'm going to need these kind of things. So in any case, these were also equivalent capacitors. So let's go back to the original one. So in that case, the idea in here is that if we have like two capacitors connected in series, then the charges on each one of them is the same. So let's just remember the argument in here. So we are saying that this plate should have 30 microcoulombs in here, which means I'm going to use a different color for the negative plate, which means I need to have minus 30 microcoulomb charge on the negative plate, because this capacitor should be charge neutral, which means on this capacitor in here, the positive plate should have a positive 30 microcoulomb. So let me put a plus sign in front. Charge in here, because these two plates are not connected to the outside, anything outside. So since they were initially charge neutral, they always remain charge neutral, whatever happens to the circuit actually. So since it's not connected to anywhere else, this is charge neutral. So as a result, since I have like minus 30 microcoulomb on this particular plate, so as a result, I should have plus 30 microcoulombs in here. And finally, we have this other plate, the negative plate is a charge of 30 microcoulombs. In any case, what's happening in here is that this charge should be the same on all of the capacitors which are connected in series, which means that they have a different potential drop. So I'm going to use a color like, I don't know, green, let's say. to write down the potential in here. So this V1 in here is basically the charge on this capacitor divided by its capacitance. So that's 30 microcoulombs, and the capacitance is 6 microfarads. So that potential difference in here is 5 volts. Yeah, I was able to calculate it at last. All right. So let's say that this is 5 volts. So that's the potential difference on this capacitor in here. I can do the same calculation again. So this V2 in here, it's the same charge, but the capacitance value is twice smaller. So therefore, we should have like 10 volt potential difference in here. So that means I think I'm going to raise this. So as a result, we have like a 5 volt potential difference across the first capacitor, and 10 volt potential difference in here. So their sum, V1 plus V2, is equal to the total potential difference. So let me just write it down in somewhere in here. So this VAB in here, so let me raise this. All right. So the potential difference VAB is equal to the potential difference on the first capacitor plus the potential difference on the second capacitor. So that's V1 plus V2. So that's 5 plus 10, that's 15 volts, just as we have expected. Similarly, we have like the potential drop on the third capacitor is equal to 10 volts, and the potential drop on the fourth one is equal to 5 volts, and we are going to get the same potential drop between A and B if I just follow this lower path in here, which means V3 plus V4 is also equal to 15 volts. I just chose the values of the capacitances symmetrically, so that's why we have nice figures. In any case, I think that's it. So I know that at this stage, all the capacitors have 30 microcoulomb charges. So that's what the question was asking. I also computed something more. I also computed the potential differences. Okay, so let me then ask this question at this point. So this is the point. I forgot the name of the point. It was the point D. All right. Sorry. Point D, and this was the point E. So what's the potential difference therefore between D and E? Okay, let's quickly compute this, but I need a new picture in here. Sorry. All right, let's just draw this picture again. This is the potential difference V1, V2, V3, V4, and let's also mark these points. So that's point D and that's point E. So I want to compute VD because the idea is something like that. So if I connect these 2 points with a wire, I know that the current will flow from high potential to low potential. Why? Well, that's basically the subject of the next chapter, but I mean, you know this from high school. So as a result, I'm not going to explain this in here. So as a result, I would like to see if this potential difference is positive or not. But to be able to find this, I need to be able to find these potentials, perhaps. I don't know. But how do you compute these kind of things? So there are actually two different ways of doing this. One of them is choosing some kind of a reference. So, for example, choose the potential at that point to be equal to 0. So let me use a different color for that. So just define the potential at that point to be equal to 0. And so therefore the potential at the point A should be 15 volts, and use the given information to compute the potential at T, for example. So you know that, for example, this V2 value, which is essentially the potential difference between the point D and point E, right, is, I forgot the value, is 10 volts. Okay, so therefore the potential at D is equal to 10 volts. And I can do the same thing for the point E. So this V4 value is equal to VE minus, sorry about this, this was point B. V4 is the potential difference between these 2 points. So therefore this is VE minus VB. So that's, we have just computed this as 5 volts. So therefore this VE is equal to 5 volts. So then you can check that, for example, this V3 is 15 minus E, and so therefore this is 10 volts and so on. So in any case, so therefore, since we established that this is 10 volts and the other one is 5 volts, so you can easily see that the D is at a higher potential than E. How much higher? Is about 5 volts. Okay, that's one way. Or you can do it like this, without setting any reference points. I can actually do it like that. Okay, but more or less I'm going to use the same kind of an idea. So I know that, for example, V1 is VA minus VD, and I know that V3 is, I need to write down these equations, VA minus VE, but I need to find the difference between these two. So to be able to compute this, I need to, for example, subtract these two equations from each other. So I'm considering these two equations. So let's do it like that. So that's V1 minus V3. VA goes away, so I get minus VD plus VE. So therefore, this is VED. It's just the opposite of VDE. So once I compute this difference, then I will be able to deduce the value of the this potential difference. So you need to write down some equations to be able to do this, but in that case, you don't need to define some kind of a reference potential. So as a result, the calculation is a little bit easier. I think V1 was 5 volts. That potential difference, this potential difference was 5 volts, and V3 was 10 volts. Let me check again. All right, yeah, I was correct. So therefore, this is minus 5. So therefore, this VD potential difference is 5 volts. Okay. In any case, so let's go back to the original problem again. All right, so we have just computed all the charges in here on each capacitor. Now we will see what happens if I connect these two. If I connect these two, then there will be a charge flow, and the charge flow will stop when it happens that these 2 points are at the same potential, right? So we are going to reach to a static equilibrium situation where there is no further charge flow, there is no further current. In this case, all the points on the conductor have the same potential. Right? Let's remember this. So we are, sorry about that. Yeah, we are in here. So we have a situation like that. But in any case, first of all, let me say this. So what do we know about the circuit? Do we know that the VAB is still 15 volts? The answer is no, because there's no guarantee that once you remove the batteries, there's no guarantee that these 2 points are still at the 15 volt potential difference. We don't know that. What we know is that basically the charge on that plate plus the charge on this plate is equal to 60 microcoulombs. Okay, because before the connection we had like 30 microcoulombs in here and 30 microcoulombs in there. So as a result, these two plates has a combined charge of 60 microcoulombs. There can be a charge movement in here between these plates, but the total charge will remain the same, and that's the principle that we must be using. Okay, So we are going to use this, but again, in here too, we have to do this analysis of series and parallel connected capacitors. So let's do it. So C and D are connected basically. You can think of them as single points. So as a result, these are like, I don't know, I mean, redraw if necessary this circuit. So you can think of the circuit like that, right? Yeah, whatever, with this part is missing, okay. In any case, so if you just do it like that, in that case, C and D just are joined at a single point, and this looks like the series connection of these two blocks in here, which can actually be expressed in here. Whatever, so let me undo all of these. So I go back to the original picture. So what I do is, I have these two capacitors which are connected in parallel. I then compute their equivalent capacitance in here. So I'm going to call the equivalent capacitance as C13. I also have two capacitors which are connected in parallel. I'm going to call their equivalent capacitance as C24. Let's just compute this. So this is like 6 plus 3. That's 9 microfarads. And that's 9 microfarads too. Okay, so in here then we have two capacitors which are connected in series, which means the equivalent capacitance is, since they are both equal, the equivalent capacitance is half of that value. So the final equivalent capacitance in that situation is 4.5 microfarads. Okay, let's come back to the original discussion. So I don't know how much charge is in here, and I don't know how much charge is in here. But when I consider these two capacitors as parallel capacitors and consider the equivalent capacitor in here, the total charge on that plate must be 60 microcoulombs. Minus 60 is on that plate, therefore 60 microcoulombs is on that one too. Okay, so what we are saying is, in that case, is that these four plates in here belonging to these four capacitors. So the negative place of the first and the third capacitors, positive place of the second and the fourth capacitors. They are charge neutral because this part of the circuit is not connected to anywhere else. So initially they had zero charge. Now they should have zero charge. Okay, so I don't actually imply that this plate plus that plate has a total charge 0. They don't. The total charge of these two plates is not 0, as we are going to find out. But the total charge on all of these four plates has to be equal to 0. But we actually see it on this picture as like this. So basically this plate, which corresponds to the total charge in these two, plus that plate, which corresponds to the total charge on these two. So the sum of the charges on these two plates has to be equal to 0. And that's why we have 60 microcoulombs on that plate in here. In any case, let's continue. I think I'm going to go one more step. So in the series connection, the charges remain the same. So we have 60 microcoulomb in here. So at this point, I can then compute. I think I'm going to use the green color in here. The new potential difference between points A and B. Right? It's basically this new equivalent capacitance. Sorry, wrong operation. So it's the charge. I think I'm going to use Q double prime in here as a symbol. You know what it is. So that's 60 microcoulombs divided by the equivalent capacitance. So that's 4.5 microfarads. I think I need to do this calculation in here. So I think I'm going to multiply both sides. Sorry about this. And then I need to divide by 3. So it's 40 divided by 3. And that's 13.3 volts. So somehow the potential difference between points A and B has decreased because of this. Let's make sure that I don't make any mistake in here. So again, I just go back. So what about this? I have like a 9 microfarad capacitor with a charge of 16 microcoulombs. So therefore, the potential drop in here. So I think I'm going to call this as V13 or yeah, something like that. So that's going to be 60 microcoulomb divided by 9 microfarads. I think I can do the calculation directly. So that's 20 divided by 3. So that's 6.6 volts. And similarly, the potential drop in here is equal to V24, that's equal to 6.6 again. And their sum is equal to 13.3. Okay. So let's note that both of these potential difference, so V13 is equal to basically VA minus VC, which is the same thing as VA minus VD, because C and D are at the same potential. So as a result, the potential difference in here, in both of these, are basically is this V13 value. So let me write V13 in here and V13. So that's 6.6 in here. So in any case, I'm just going to then compute this. So I was going to find the charge on this plate and charge on that plate. So let me do the calculation quickly in here. So this Q1, the charge on this plate is equal to the capacitance value multiplied with the potential drop on the plates. So that's V13. This is therefore 6 multiplied with, yeah, let me write down the units. Yeah, forget about the units. 6 multiplied with 6.6. So let me write down this correctly. So 6.6 was 20 divided by 3, so that's going to be 40 microcoulombs. Okay, so for this one, the charge is equal, so that's the new value of the charge. So let me put double prime in here. I think that's better. In any case, the charge in here would be C3 times V13. So that's 3 times 6.6. So that's going to be 20 microcoulombs. Okay. So let me quickly continue with these. So this is the charge in here is Q2 and the charge in here is Q4. I'm just going to write down the values in here so you can easily multiply these. So that's going to be 20 microcoulombs and Q4 is equal to 40 microcoulombs. So I think I need to put double primes in here. Okay, so as I have said, the charge on this plate, which is minus 20 microcoulombs, minus 40 microcoulombs, sorry, and the charge on that plate, which is plus 20 microcoulombs, their sum is not equal to 0. The reason is that there has been a charge flow from point, sorry about that, this should have been point D. Yeah, there has been a charge flow from the point D to point E, right? Sorry about this, I got all the symbols confused. In any case, so because of that, these two plates, they don't have 0 total charge anymore. And from here, I can deduce the amount of the charge that has flowed through. So let me kind of show it, summarize the results like that. So initially, we had these 4 capacitors where the charges were this Q1, Q2, Q3, Q4. So all of these values were equal to 30 microcoulombs. And then there's a change that happened. So something has changed. So the circuit has changed. And so we now have a circuit like this, where these 2 points are connected now, in which case I call the charge on these plates. So these are basically the charges on the positive plates, because I know that the charges on the negative plates are the negative of these. So these have new values now. So that's Q3 double prime, and this is Q4 double prime. I think I have just found that Q1 double prime and Q4 double prime are the same. So these are 40 microcoulombs. Was it? Yeah. And yeah. Okay. And Q2 double prime and Q3 double prime, these are 20 microcoulombs. Okay. So that means when I make this connection, there were some charge flows on the circuit. So definitely, I mean, there were some 30 microcoulombs on this plate. After the connection, now the charge is 40 microcoulombs, which means a 10 microcoulomb has flown from the positive plate of the third capacitor to the positive plate of the first capacitor. So that's 10 plus 10 microcoulombs has flown over this edge like that. All right. What about this part in here? So just consider the amount of the charge in here. So initially that charge was equal to 0, because we had like minus 30 microcoulombs on this plate and plus 30 in here. So initially the total charge was was equal to 0. After the connection, the total charge in here was minus 40 in here, plus 20 in here. So the total charge is minus 20, which means 20 microcoulomb, yes, 20 microcoulomb of charge has flown from this upper region to the lower region over the wire that we have just attached. Okay, on that side, I think you're going to find out that on that side there's a charge flow along that direction, which is also equal to 10 microcoulomb in here. So as a result, there are some charges that leave these lower capacitors, which is basically plus 10 and plus 10. But there are some additional charges that come into these two capacitors. So they still remain charge neutral. So as a result, the total charge that has flown from all sides into these all 4 places of these lower capacitors is equal to 0 in that case. So as a result, this 10 plus 10 is equal to 20. Okay, I think I'm going to go with the final calculation in here. So that's basically the energy. So I'm going to call the initial energy in here as UI, and the final energy is in here as UF. And by just explicitly computing these two, I'm going to also show that the final energy is smaller than the initial one. The energy is decreased by that connection process. This actually implies that there was some part of the initial energy is converted into heat during this connection process, and this heat is basically appeared on the resistors, but this part of the physics we haven't seen yet, so that's actually part of the next chapter or the following chapter. So we will talk about these, about the dissipation on resistors. But in any case, so the final energy should be smaller than the initial one, because this is just a spontaneous process. It cannot take energy from outside, but it can give energy in the form of heat. Right? Let's just do the calculation, but I think I'm going to do it like this. So this was the initial configuration. I just said that I can think of this all of the 4 capacitors in the initial configuration as one equivalent capacitor with a capacitance of this much, and it has this much charge, and this was a potential difference. But in any case, so the initial potential energy can be written as basically the capacitance of the capacitor, the equivalent capacitance of the system multiplied with the potential difference squared. Okay, so this is 4 microfarads, and the potential difference is 15. Yeah, I need to take the square of 15. So I think I'm going to do it like this. So that's like this is 900. So as a result, this is 450 microjoules. Okay, so that's the initial total energy. I'm going to do the final, compute the final total energy now. So in the final situation, this is the equivalent capacitance. Yeah, the potential difference is complicated now, so I don't want to use it, but I know the total charge, so as a result, I'm going to use this expression. So the final energy is equal to 1/2 of the charge squared divided by the capacitance. The charge is 60 microcoulombs, microcoulombs squared, and capacitance is 4.5 microfarads. There are a square of micro divided by a micro, so there is always one micro in here, so the result is microjoules. But let me write it down like that. So that's like 3600 divided by 9. Yeah, I forgot how to divide numbers. So this is 400 microjoules then. Okay, so then let's come back to this calculation in here. Where was it? Yeah, so the initial potential energy was 450 microjoules. Final potential energy is 400 microjoules. So that's the electric potential energy. So we can see that the change in the potential energy is negative. So that means, well, some electrons in the environment or some atoms in the environment has some increased potential energy. Well, this is basically converted into heat. Right? So first it's converted into the kinetic energy of the charge carriers, then eventually it is converted into heat. The fact that, we were expecting this quantity to be positive, and yes, so it appears that probably we haven't made any mistakes so far. Okay.